this online talk. Your attendance is greatly appreciated. As a reminder, Chaos's new talks rep Eden will be hosting a Q&A session at the end, so please feel free to leave any questions in the message function, I think, sort of section. I'll put a message in there in a second anyway, but just leave those in there and Eden will go through those at the end. It's my pleasure to welcome and thank Nick, Daniel and Nikolaus from UKAEA for joining us today. Nick is a Bath graduate who went on to complete his PhD research at York, who will be leading the talk alongside Daniel, a current year in industry student. For context, Nick's time with UKAEA started with a 6-month internship during his undergraduate study, which progressed to 2 fellowships and finally a permanent position. His research is primarily focused on turbulence in the plasma edge, the part that separates the hot fusion core from cold material surfaces in a tokamak. He was also the recent recipient of the inaugural Malcolm Haynes Award for Early Career Research from Institute of Physics. So without further ado, I'll pass straight over to Nick, who you're all here to hear talk about. Excellent. Thank you.
Thank you, Will. So yes, this will be experimental in a few different ways. There will be audience participation. So, can everyone hear me? Hello?
Yeah, I can hear you.
I can hear you.
I can hear you.
Oh, thank you. Sorry, all the videos on my end just completely froze up for a second. Okay, brilliant. I'll keep going then. Yes, so experimental in a number of ways. Partly because there's going to be 2 of us talking, so I'm going to hand over to David for a few slides. We thought it'd be nice to give to let David tell you a bit about fusion, as he is one of your own, we thought that'd be a nice touch. Also, there will be audience participation. Please have a smartphone or a web browser or something like that ready, and prepare to answer a few questions just on a couple of little questions to get us all thinking. Okay, so without further ado, I like to start my talks with this picture, which is perhaps a bit scary. I like to start my talks by talking about climate change, and I think this picture encapsulates a lot of the kind of approaches that a lot of people have to climate change. It certainly and sadly is mine. I always give my own background as an example. So I work in clean energy. I'm passionate about climate change. I understand that it's a problem in the analogy here, the house is on fire and our world is on fire. But I still drive a diesel car. I still drive fossil fuel. I still burn fossil fuels. And I don't have any plans to buy an electric car at the moment. Kind of like this gentleman whose house is on fire and his answer is to mow his lawn. And I think that there's good reason that this kind of reaction is standard. And that's because it's really a very intangible thing. It's a very intangible problem. And it's hard, I think, to really get a grasp on what we mean when we say climate change and what kind of problem we're trying to solve. To think about that a little bit, here is your first bit of audience participation. So if you could, on your smartphone or on your web browser, go to this website here, www.menti.com, and use this code 93864. I'll give you a couple of minutes, or I'll give you a few minutes to do that. Then answer this question: how many tons of oil, and I mean equivalent tons of oil, so what is the equivalent amount of tons of oil, how many tons of oil did we burn in 2018 in fossil fuels? And can I just check, can you see my web browser now?
Yeah, looks good.
Excellent. So we have 5 answers so far. And this is so this is what I mean when I say this is a real existential problem, because none of these numbers are particularly small, right? We're talking about tons and tons of oil burnt here. Oh, thank you for whoever put that in the chat. That's very helpful. I didn't think that one through, although it is at the top of the screen here. Okay, I can see that a fair few answers are starting to filter in now, and 14 of you are correct. So it was around 10 billion tons of oil was burnt in fossil fuels alone in 2018. And this is what it looks like when we, this is what that actually looks like. This is a prediction from the International Energy Agency on how much energy we will use or have used and how much energy we will use in 2014. In 2018, actually 11 billion tons of oil equivalent burnt in fossil fuels. Now, the prediction is that our use of energy will increase up to 2040, and this is largely because of population growth in centres like India, China, Africa. But actually our dependence on fossil fuels may start to level out. So this 11 billion tons doesn't grow significantly to 2014. But we know now, because of all of the catastrophic impact that this will have on climate change and on our society and way of living, that this is not what we need to do. This is what we need to do. We have to be able to sustain this growth in energy demand whilst simultaneously transitioning to a zero carbon energy market. So that means, in very simple terms, we have to displace, or we have to replace 11 billion tons of oil equivalent with some other form of energy to get to this zero carbon. And we don't just have to do that. We can't just do that for 2040, because it's no good doing it until 2040 or 2050 and then having this curve expand back out again. That's no good at all. We need to come up with a solution which allows us to displace this amount of oil for the rest of humankind, for the rest of society's history. What we would like to be able to do is we would like to displace this fuel with something that is safe, something that is renewable, or sorry, not necessarily renewable, something that is abundant, something where the fuel source, we don't need to worry about the fuel source, something that is carbon neutral, and importantly, something that is baseload. And by baseload, I mean something that will run continuously as and when you need it. Fortunately, we have that. So we have that in the sun. The sun is a fusion reactor, and we've known that the sun can do fusion for many, many years. And it was this chap, Sir Arthur Stanley Eddington, who in the 1920s was pondering, how does the sun stay hot? What powers the sun? And he came to the conclusion that the reservoir, and by reservoir he means the source of energy inside the sun, can scarcely be other than the subatomic energy which exists abundantly in all matter. So what he's talking about here, of course, is E equals delta mc squared, which is energy is the change in mass times c squared. This is the famous Einstein energy equivalence relation. We sometimes dream that humanity will one day learn how to release this energy and use it for their service, since this store is well nigh inexhaustible, if only it could be tapped. So he's pointing out there that there is this potential to use fusion energy for humankind's service, if only we can actually get that energy out. This was met with a lot of skepticism at the time, so lots of people didn't believe in fusion. It wasn't that long ago before Eddington came along that people still considered that the sun might be running on coal. So there was some skepticism, to which Eddington replies, "We do not argue with a critic who urges that stars are not hot enough for this process. We tell them to go and find a hotter place." And I always say that it's a shame Eddington isn't alive today, because actually, of course, with all the scientific developments since the 1920s, we now know that there are lots of hotter places than the sun in the universe. We even know that there are hotter places than the sun in the solar system, one of which is here. So this is JET. This is at our lab in Culham campus in Oxfordshire, which, as Nick said at the start, if you ever have a chance, please come down and visit. It's a really wonderful place to come and visit. And inside this building is JET. And inside JET, we do fusion regularly, and we get up to temperatures that allow us to do fusion and produce energy. So what is fusion? I like sci-fi, and I always like to show what sci-fi thinks fusion is. So in the 1980s, sci-fi thinks fusion is this machine that you can put on the back of your DeLorean and chuck banana skins into. Not quite true. Sci-fi in the 2000s thinks fusion is a tiny device that you can plug into your chest and power your suit of armor. Again, not entirely true. And I have to say, I would not want to be putting a fusion reactor in my chest. That is horrendously dangerous. But we can build fusion reactors. It doesn't look like this. But we can build fusion reactors, and we know how to do it. We now know what fusion is. So what actually is fusion? Fusion is the process that powers the stars. And many people will have heard this idea that the sun is a ball of burning gas. Not quite true. So at low temperatures, a gas, it looks like this. So you have a central nucleus, you have an ion at the center of your atom. These are orange here. And around that ion, you have these electrons that orbit around the ion. It's a bit more complicated than that. I'm not sure how many of you have, how far through quantum mechanics you all are, but it's certainly more complicated than this picture shows. But essentially, this is what a gas is. If you heat a gas up, these electrons gain a lot of energy. They start vibrating around, moving around very, very fast. They become liberated from their atoms, and they do this. And all of a sudden, you end up with this really interesting state of matter where all of the electrons are moving around independently of all of the ions. And this is a plasma. It turns out actually that something like 97% of all of the matter in the known universe is actually in the plasma state of matter. It just so happens that here on Earth and on planets, conditions are not conducive to creating plasmas. So we don't see plasmas in our everyday life, but for the rest of the universe, plasmas are absolutely commonplace. Now, of course, ions are charged. So you try and push an ion together and it forces, and they repel each other. You try and push them together even harder and that repulsion gets even stronger. However, if you can get them so close that they're touching, then the strong nuclear force takes over from this mutual charge repulsion and binds them together, and they become so strongly bound they form new nuclei. So the challenge is, how do you get these ions to close enough that they bind together and they fuse? And to do that, you have to heat them to enormous temperatures so that they're moving around really, really fast and they can collide with one another. And that's why fusion is hot. Now, it turns out that actually fusion in the stars is a really inefficient process. We would not want to do fusion on Earth based on these kind of fusion cycles. So in stars like our sun, this cycle on the right is what powers them. In heavier stars like Betelgeuse, this process on the left is what powers, what tends to power the star. But I don't want you to pay any attention to these processes in any great detail. All I want you to do is note that in the right-hand side, we have to go 1, 2, 3, 4 different processes to get from here to here. In the left-hand side, you have to go through 6. Now, each one of these processes is really, really rare. It's like rolling a dice with billions and billions of sides. And what I want to do here is I want to roll that dice 4 times and get the same answer 4 times, so that you can see that that is an extraordinarily rare event. So fusion in stars is not efficient. If we want to generate energy from fusion, we have to do better. And I will just take this moment to get you to go back to your smartphones, back to your web browsers, and answer me this. Knowing that fusion in the stars is so horrendously inefficient, what do you think is the record for fusion energy gain on Earth? And by energy gain, I mean how much power we've got out of fusion compared with how much power we've put into fusion. And if by magic this works, let me just move this along one. So how much energy do you believe that we have got on Earth from fusion? How much energy gain, sorry, do you believe that we've got on Earth from fusion? That's power out over power in. It's a very interesting, interesting problem, this. And lots of different fusion labs have creative ways of defining energy gain. So you might have seen in the news in America, for example, they have a fusion lab which claims that they'd got more power out than they put into fusion. But the way they managed to do that was some really creative, essentially a creative accounting for how much energy actually went in. They decided not to count all of the energy that goes into all the systems to make the machine running, and only count the energy that went into the hot bit of the fuel to create the fusion. So if you count everything all together, then actually they only got about 0.0006%. However, We on Earth have got much better than that. And the correct answer here is 65%. So 26% of you, well done. In 1997, the Jet Tokamak, which I'll talk to you a bit about later, was successful in achieving 65% of all of the power that we put into the process back out as energy in high power neutrons. And I'll tell you a bit more about that later. And it did it by using a different fusion reaction. So we don't use hydrogen in our fusion here on Earth. We use a different fusion reaction, which I can show you here. So this is what the inside of Jet actually looks like. And I'll show you this video again a bit later. Inside Jet, we don't use hydrogen. We use two isotopes of hydrogen. We use deuterium, which is 1 proton and 1 neutron. And we fuse that with tritium, which is 1 proton and 2 neutrons. Now these fuse and they form helium, which is 2 protons and 2 neutrons, and a single neutron. And it's the energy in that single neutron that we're going to harness to be able to get energy back out of the process. Now, deuterium is really abundant on Earth. So something like 1 in every 6,000 hydrogen atoms in water is actually deuterium. Tritium, on the other hand, is a bit difficult. So tritium is a radioactive isotope of hydrogen. So it comes in gas form, but it's a radioactive gas. So that means it doesn't form naturally on Earth, because within 12 years, you lose half of all your content. So we have to do something different. And actually, we use lithium. So lithium, if you take lithium and you bombard lithium with neutrons, and bear in mind, neutrons is not something we're short of here. If you bombard lithium with neutrons, you can produce tritium as a byproduct. So it turns out, if you took a bathtub of seawater and a laptop battery's worth of lithium, you have enough potential energy yield from fusion, from the lithium and the deuterium in those two devices, to displace 40 tons of coal or 250 kilograms of processed uranium ore. So the energy yield from fusion is really quite enormous. The challenge is, how do we get the fusion conditions here on Earth so that we can do that in a sustained manner? And we can do that, we can get hot enough, we can get dense enough in order to produce more energy out than we put in. So, David, I'll hand over to you. I will mute myself and hand over to you.
Okay, thank you. So we've seen how fusion happens in the sun, but how do we replicate that on Earth? There's a simple recipe called the Lawson criterion, which we have to satisfy to get a net energy output from a fusion reaction. And we need to satisfy this inequality to get past the break-even point. So in this triple product, we have N, which is the density of the fuel, T, the temperature of the fuel, and tau, which is the confinement time, how long we keep the fuel in one place. Since we're only putting in 2 grams of deuterium and 2 grams of tritium, it's quite low density, but when we heat it up to 100 million degrees centigrade, that causes a huge pressure buildup in the center of the machine. And we need to contain that highly pressurized plasma for long enough to get some meaningful energy output. For fusion to be a viable energy source, we need to get more energy out than we put in. So the Lawson criterion, you could think of as a condition we need to satisfy to make fusion a viable energy source. So magnetic confinement fusion does what it says. We're using magnetic fields to confine the plasma and maximize that confinement time in the Lawson criterion. So you'll know from electromagnetism that the force on a charged particle due to a magnetic field is its charge times V cross B. That cross product means that if a particle is traveling in the same direction as the magnetic field, then it will feel no force. So if we create some magnetic field lines that loop round on themselves, then we'll be able to keep the particles moving in a loop and keep them confined. And that's the main principle behind magnetic confinement fusion. So there are a number of designs for fusion reactors, and the most advanced design is called the Tokamak. That's the type of reactor that we use at UKAEA, and that's where we have the world's largest tokamak called Jet, which Nick has already mentioned. The name tokamak comes from these Russian words, which mean a toroidal chamber in magnetic coils. Toroidal means it's like a torus or donut shape. So we need to keep the plasma away from the walls because it's so hot that if it came into contact with the walls, it would vaporize them. And it would also cool the plasma down, which means we don't get as much fusion happening. So because everything in the plasma is charged, we can use magnetic fields to affect it. These magnetic field coils around the outside of the machine create a helical magnetic field, which loops around the inside of the machine. And these coils can be used to shape the field, and therefore we shape the plasma. All of this needs to be done inside a vacuum vessel because the impurities that we might introduce from the air, like oxygen and nitrogen, which ended up in the plasma, would heat up and radiate light away, and that causes the plasma to cool down. So in summary, we've got a vacuum vessel that's surrounded by some magnetic field coils, and we call that a tokamak. Back to you, Nick.
Naturally, I was muted when I tried to talk then. Thank you very much, David. That was excellent. And you can all grill David when he gets back to Bristol next year and comes back to all things Bristol physics. So you know what a tokamak is, and you know how cool tokamaks are now. This is JET. So I was just saying, JET holds the record for fusion energy. In JET in 1997, we produced 65% of the power out that we put in. And this is what JET looks like on the inside. So JET is a joint European venture. So all of Europe have come together to build JET, but it's located at our lab in Cullen. And JET was built, well, JET started to be designed in 1978, came online in 1983, and it's been running ever since. And JET is a really phenomenal machine. It's the biggest tokamak in the world, and it's the best place to do fusion in the world. I'll show you a video of JET. So one thing that I really like about this video is as we watch it going up, you can see basically the areas where you see a lot of light are the areas where the plasma is coming into contact with material surfaces. And when this really gets going, you can see in this video that you have a lot of speckles. You have speckles all over this video. And these look like something going wrong with the camera. And they are, but not for any fault of the camera itself. Let me just play that again. So what's going on here is all of the fusion-born neutrons that are being produced in the fusion processes inside JET are coming out and they're hitting the camera sensor and they're killing the pixel on that camera sensor for a split second. And I think this is really cool because we can actually see fusion happening here in JET. And JET does fusion for a living. The last time it did a real fusion campaign was back in the 1990s, but we're now gearing JET up, subject of course to pandemic and lockdown and things like this. We're now gearing JET back up to start running fusion experiments again. So you should expect to see more fusion experiments coming out of JET. Well, I normally say later this year, but probably more like next year, in the next couple of years now. So it's a really exciting time for JET and a really exciting time for fusion. Now, there's this old adage that fusion is always 20 years away and it will remain 20 years away for the next 20 years. And to some extent that's justified, but I'd like to open up for a third question, which is if we think that fusion is always 20 years away, how many years does it take for us to double our fusion performance? By which I mean, how often, how many years does it take for the world to get twice as good at doing fusion? And this is your third and final piece of audience participation. Thank you very much for bearing with me. So, how many years does it take for fusion performance to double? And this is throughout the whole world. How often do you think fusion performance doubles? So I'd say we've got two camps at the moment. We've got some skeptics, some optimists. One real optimist there, I like it. One real pessimist there. Good. I think we've got a real good spread of results here. Excellent. That was just what I was hoping. So how long does it take, how many years does it take for fusion performance to double? Now, I've got a really good graph for that, and that's this one here. So some of you might be familiar with Moore's law. If you haven't heard of Moore's law, I'll run you through it quickly. This is this orange line you can see here. Moore's law tells us that every 2 years, the performance of our computer chips doubles. So our computer chips get twice as fast every 2 years. And you can see that that's held true for many, many years. It's a real interesting feature of technological development, and that's remained true right up until the 2010s. We can do the same thing for fusion. So we can measure this thing that David introduced you to earlier, the fusion triple product, say how close to doing fusion are we? And we can measure that. And if we take the very first tokamak, T3, that was built in Russia, and we do that all the way up to the 1990s, when JET was running its fusion campaigns, you can see actually we're faster than Moore's law. It turns out that fusion performance doubles every 1.8 years, or at least it did so until the 1990s, until JET set this fusion record. So whoever said, the 5 or 6 of you that said 1.8 years, congratulations. You are the perfect balance of optimistic and pessimistic. You are not glass half full, not glass half empty, but the glass is just half wonderful. But what's going on here, right? So we get to this fusion record in JET, and then nothing happens. And ITER, which I'll talk a bit about in a second, is the next stage in fusion, and ITER will produce net fusion power. Why do we have this gap? Well, let me break it down for you this way. So in the 1960s to the 1990s, all of these things were concept-defining experiments. Their goal was to just do fusion better, right? It was to get better and better, get higher and higher performance. But we got to JET, and we got to the point where we're reasonably confident that we can do fusion now. The fusion side of stuff is done. What we now need to do is build all of the other aspects that make a fusion reactor a fusion reactor. And there are a lot more complexities in building something that will produce energy than there are in building something that will just do the experiment. And that's what we're seeing here. So this apparent delay in progress is not a delay in progress at all. Actually, what's going on here is us saying, well, we can do fusion. Now we need to come up with ways of making sure the machine doesn't destroy itself, of making sure we can repair the machine in a way that doesn't harm humans, make sure we can handle tritium, building the machine out of suitable materials. And this is what's going on now. So we've never really been, this whole idea of we're 20 years away from fusion is complete nonsense. The progress that's been made in fusion is extraordinary, faster than Moore's law, faster than particle accelerators. And we're now in the era that we call the delivery era. So this machine, ITER, is just monumental. It's being built in the south of France, and it's a collaboration between these 7 different entities. So China, European Union, India, Japan, South Korea, Russia, and the United States. Interestingly, you look along this list of names, not normal bedfellows. So you can appreciate some of the complexities that have already gone on just to get this off the ground. ITER represents about 50% of all of the world's population. And more interestingly, ITER represents about 90% of all of the world's economy somewhere in one of these nations. So it really is a completely global collaboration to make fusion happen. And ITER will do that. So the headline goal of ITER is to do this thing, produce 10 times more power out than we put in. So produce a 10 times power gain. And I believe ITER will do it. It's being built right now. It's about 70% complete. It's due to run its first plasma in 2025. And we're very confident that ITER will work. But let's put this into some context. ITER is monumental in every way. It's about as big, the total site is about, or the total building is about as big as Wembley Stadium. The heating systems on ITER are strong enough that if you put a car in front of one of them, it would vaporize in 16 seconds or so. The magnets on ITER are so strong that if you put the central magnet on ITER above an aircraft carrier, like a naval aircraft carrier that sits on the ocean, and you ran it, the impulse from that, the the impulse from that magnet would be enough to levitate that aircraft carrier out of the ocean. So the technology is immense, and we're doing it. The problem is that it's expensive. So So the technology is immense, but we're doing it, and we're on this step ladder. So we have JET now, we have ITER in the 2020s, 2030s, and then we need to go on and build something that actually connects to the grid, that actually produces usable electricity. We call that demo, which is shorthand for demonstration. The problem is that ITER is expensive. So ITER is going to cost around 25 billion euros, which is about the same as 4 or 5 large hadron colliders. So it's very, very expensive. And that begs the question, is there a cheaper alternative? So in the 1970s and 80s, people started to investigate this alternative approach, which is called the Spherical Tokamak. And I show you a comparison down here in the bottom right-hand corner. So a regular tokamak, like ITER, like JET, looks like this donut shape. A spherical tokamak looks like you've pushed everything much, much closer to the center of the machine. It looks a bit more like a cored apple. Now, why might you want to do this? Well, it turns out the really expensive parts of a tokamak are its magnets and the amount of the building that you have to pour with nuclear grade concrete, because nuclear grade concrete is expensive. It has to be able to shield, it has to be shielded against all of the nuclear reactions that are going on inside. So if I can make my machines smaller, I can make the magnets that sit around my machines smaller, and I can make the building that sits in, that has to be coated in nuclear grade concrete, smaller. So I have this, and if I can do everything in this smaller amount of space that I can do in this larger amount of space, then I have a route to making a reactor that is cheaper than the conventional approach. And in the 1980s, this concept started to take form in reality. And this is START. So START was small tight aspect ratio tokamak. This was built at Culham in the 1980s. And its bigger brother is MAST. MAST is the megaamp spherical tokamak, which came online just before the millennium. So it came online in the late 1990s, early 2000s, and it ran for about 13 years. In 2013, we shut down MAST, and it began disassembly because we're now building a brand new machine called MAST Upgrade. Now, this is called MAST Upgrade because it is essentially, the concept is the same as MAST, and these red parts here and this outer can-like structure is all the same. But everything on the inside, about 95% of everything inside the machine is brand new. So really, this is almost a brand new machine. It's just in the same, essentially dressed up the same. This is what a plasma will look like on the inside of MAST Upgrade. And these are a few pictures of it being put together. So this is what the inside of the machine actually looks like. This is a photo. This is the top going on. This is the can being fitted onto the bottom of the machine. And again, this is a view inside the vessel. This is really exciting. And it's really a world-leading experiment paving the way for the spherical tokamak going forwards. So, and on the back of all of this experience with spherical tokamaks, the UK government and UKAEA have started a program called STEP. You may or may not have heard of STEP. So STEP is called Spherical Tokamak for Energy Production. And STEP is one of these demonstrator concepts. So STEP is, the idea behind STEP is, can we build a fusion reactor that will produce energy based on the spherical tokamak approach? Can we use it to make a more economic way of building a fusion reactor? And STEP will run over the next, so STEP is currently in its first phase of its program, where we're building, where we're coming up with a concept design. So we're just a preliminary concept design. In the second phase of the program, it will develop a detailed design. And in the third phase, it will be built, constructed, and go into operations. We hope that we aim for STEP to be producing electricity on the grid, on the national grid, by 2040. That's the aim for STEP. It's really exciting. It's probably the most ambitious domestic fusion program anywhere in the world. There is nothing that really comes close to this as a single domestic fusion program. And it's really, really exciting that we have the support from government to do this, and we have the will to be able to bring this forwards. So what kind of challenges stand in the way of something like STEP? Well, we think ITER will work, right? But we know that ITER is not really big enough or cheap enough to produce meaningful energy. So what do we have to do in order to make that better? We think there are 6 kind of main technical challenges that underlie fusion. I'm going to go around them very quickly. So burning plasmas, number 1, how do you get the hot bits hot, and how do you make sure they stay hot enough for long enough to do a meaningful amount of fusion? 2, can we build a machine out of materials that can withstand the fusion environment? So the neutrons that you produce from fusion are very, very damaging to materials, right? They're moving around with really high energies, they hit materials, they do damage, and we need to build our reactor out of materials that can withstand that. 3, we've got the hot stuff hot, so we can do a large amount of fusion, but once the fusion is done, or whilst the fusion is ongoing, there is a lot of heat that is excess that we can't use to make electricity, but we still have to dump somewhere. How do we remove that heat from the machine without damaging any kind of material components? Excuse me. Number 4, we have to be able to run this machine with deuterium and tritium, but tritium is not abundant, so we have to create tritium. So that means that we have to be able to run the machine completely self-sufficiently without having to inject any other tritium in. So there's only enough tritium in the world at the moment, in the entire world, to start up 1 tokamak reactor. So we could do that for demo, for example, or we could do that for step, but we would never be able to do it again. So these machines have to be completely self-sufficient. Number 5, it is really not conducive to your health to stand next to one of these machines when it's operating, right? There's X-rays going everywhere, neutrons flying everywhere. Your small squishy bodies will not appreciate that kind of environment. So we have to do all maintenance activities, repairing, servicing, etc., decommissioning with robots. And that technology is really in its infancy. So we have to develop all of that kind of technology to be able to do all of these tasks completely remotely. And finally, number 6, if you can do all of these top 5, brilliant. But you have to be able to do all of them in a way that they all fit together into one holistic, synergistic picture of a fusion reactor. It's no good developing a way of removing your excess heat that you can't service robotically, or developing resilient materials that don't breed enough tritium. So you have to do this all together, and that is a challenge in its own right. And just in the last sort of 4 or 5 minutes, I'm going to go and give you some examples of some of the really exciting stuff that we're doing just on 3 of these topics. At UKAEA, we study all of these topics. We have really active research in all of these areas. I just don't have time to take you through all of them, so I'm going to show you a top 3. So burning plasmas on JET. I showed you a picture of JET running before and producing fusion. And I told you that JET has produced 65% of the power out that we put in. Oops, excuse me. Now, if you're looking at this graph, if I take this black line at this point here averaged over about 0.5 seconds. If I took this black line and I extrapolated it to using deuterium and tritium, this black line would produce this record of 65% of the power out that we put in. So this black line represents what JET used to be able to do. Now in 2011, we actually replaced all of the inside of JET. So when JET got this fusion record, it didn't look anything like this. It was all made out of carbon and graphite. Now it's all made out of metals because that's what ITER will be made out of. And when we did that, we saw that actually it was really hard to get back up to this black line. So these red and blue lines are about how, these red and blue lines show how we were doing in 2016 at trying to get back up to here. So this is a real challenge, right? Because what we want to do is actually, when we run deuterium and tritium again, we want to get to this yellow point here. We want to either increase the duration that we can keep this record fusion production going, and simultaneously increase the yield of these points down here so that we get up to there. And these stars show you our current progress towards that. So we're doing well. We're starting to get back up to our old performance levels. And here at 5 seconds, we're now actually hitting records. When JET was operating, we were hitting records almost day by day, showing for how much fusion, how many neutrons we were producing. And we were really working hard to get back up to this target. And the focus of JET now is to take these stars and get them to this point here. And when we can do that, we can then run a deuterium and tritium campaign and be reasonably sure that we can prove that we can have this kind of performance in JET where we don't just get the record for a blip we can now get the record, we can sustain the record, we can keep it going. And when we can do that, we can be reasonably sure that we've operated Jet at its absolute peak performance. So that's the goal now, and we're well on the way to doing that. Now, heat removal, Mast Upgrade is probably the world's best machine for studying this problem. So these chambers that you can see at the top and the bottom of Mast Upgrade are a really, really innovative thing. I'm just going to go take a step back here and give you a bit of a history of Mast Upgrade and STEP. So the Spherical Tokamak, when it came along, we showed that you could operate this machine, you could probably get to fusion relevant conditions in this machine. But if you imagine that I've taken a machine like Jet, which can do fusion and has all of this excess heat in it, and I've pushed it all much, much closer, I made it much, much smaller, the amount of heat now that I've got is being concentrated on a really small area, which means that it's really, really intense. So it's a really hard problem to solve. So whilst this makes things cheaper, it actually makes the issue of removing heat a lot more difficult. And in 2007, we had to sort of say, okay, fine, we accept that this is a problem and we can't do anything about it. But then people got their thinking caps on and said, okay, well, how do we solve this? And the solution we came up with was this thing called the Super X diverter. And that's what you're seeing here. So these chambers in the top and the bottom of the machine, these are where we're planning on putting all of the plasma with all of the heat in it that we no longer can use. And I'm showing you in this left-hand plot here, in this left-hand animation, what the temperature of the plasma looks like as we're putting it down into this chamber. And one really interesting thing you can see is that as we fuel the machine more, the temperature in the core where the fusion happens stays hot, but the temperature down here in this chamber where we touch materials gets colder and colder. And this is exactly what we want, right? We want a situation where the hot stuff in the fusion core stays hot, but the cold stuff that's connecting to a material surface gets colder and colder. So this is modeling, this is a simulation. And when Mast Upgrade comes online, again, this was written some time ago, so probably coming 2020, possibly 2021, depending on lockdown. When it comes online, we hope to prove that this concept works experimentally. And once we can do that, we've got a really clear route then to building a Spherical Tokamak fusion reactor, because we've shown that this real absolute critical problem has a solution. So that's what Mast Upgrade is doing, and that's why it's really, really exciting. And finally, robotics. So we don't just do plasmas down at Cullen, we do all of the problems. We do tritium, we do materials, and we do robotics. And I like to show you this video because things like cutting a pipe sound like it should be quite an easy job. But when you can't put humans in the loop, cutting a pipe becomes a very hard job. And this little video, this little animation, gives you an idea of how we think we might be able to use 3 robots working in tandem to cut a pipe. So this snake robot goes inside the pipe and it gets to the joints that you're planning on cutting. Once it gets there, it locks itself in place with these ball bearings that stick out, and it's got a laser, rotatable laser, that rotates around and cuts the pipe. Simultaneously as it's cutting the pipe, it collects all of the nasty bits that fall off, all of the welding material that comes out. And once it's done, it retracts itself back out, and you've got a cut pipe. And all you need to do then is take the section away and replace it. So this is a way that we might be able to have remotely operated robots cutting pipes. Now this looks great, right? It's a lovely animation. It looks like science fiction, right? Well, actually, these things we're already building. So this is one of these laser robots. This is the pipe that it went into, and these are 2 pieces of a pipe that this laser robot was able to cut. So we're thinking about solutions for these problems right now, and we're building robotics to solve these solutions for all of these problems that are really, really non-trivial and are fundamental to making a fusion reactor work. So we've gone to all this trouble. Hopefully I've convinced you that fusion is really cool, but let's recap. Why do we actually care? Why do we care so much about fusion? Well, fusion offers us the chance of having a continuous power supply. It doesn't depend on the wind. It doesn't depend on the sun shining. We can turn it on and off whenever we want. There are only small amounts of long-lived radioactive waste that come out of fusion. It's not true to say that we don't produce any radioactive waste, but the amount we produce is really quite inconsequential in comparison to a nuclear reactor, and even in comparison to fossil fuel type stations, which also produce small amounts of nuclear waste. There's no carbon byproducts in this reaction, right? So we do not produce any carbon from the fusion reaction. Now, there is carbon that we will spend in, well, unless society can go somewhere to electrify and construction and supply, we will spend carbon to pour concrete, we will spend carbon to build the machines. But because there's no carbon in the process, we can become carbon neutral if we operate for long enough. The fuel source is absolutely plentiful. We've got enough fuel here on Earth in lithium and deuterium to last us about 1 million years or so. And if we haven't come up with a better solution in 1 million years, then I don't think we deserve to keep going forwards. And finally, really importantly, it's very, very safe. So we don't have a kind of meltdown scenario like you do in fission reactors. We don't have nasty byproducts that go in and pollute the air. So fusion is a very, very safe alternative to these fuel supplies. And if you don't believe me, hopefully you believe this man, Stephen Hawking. So in the very last interview he did before he died, he was asked, what world-changing idea, small or big, would you like to see implemented by humanity? And he said, this is easy. I would like to see the development of fusion power to give an unlimited supply of clean energy. And this is one of the brightest minds that's ever lived, saying how important fusion is to humanity. So hopefully I've convinced you that we're well on the path to a fusion future where we build something that looks like this, a fusion power plant that is providing clean, safe, renewable, abundant energy for the future of humanity. If you want to find out more, there are loads of different ways of accessing information about fusion. All of our social media, these are various email addresses that you might be interested in. If you're interested in working in fusion, you're welcome to contact any of these email addresses. You're welcome to ask for me by name, and I'm more than happy to get in contact with you. And we'd really like to know what you thought. So if you want to drop a line to any of these things and just share your thoughts on this talk, that would be we'd be very grateful. And I think I've even left some time for questions and answers. So thank you very much for bearing with me. Thank you very much for your for participating in my risky audience participation strategy. And I guess I'd like to now open up to Eden for questions and answers.
Wow, thank you so much. That was an incredible insight into fusion and the work at UKAEA. Thank you so much. And also you, David, as well. And of course, Nick and Will, our other talks rep, who has just made this our first virtual talk possible. So yes, questions. I'm sure everyone does have them. You haven't put any up in the chat window yet, but do start typing your questions up and then I'll ask them. But I mean, I thought I'd start with a question. I was just, why are stars so inefficient in fusion?
Okay, yeah, I'm not muted. That's a good question. I guess the reason that stars are inefficient is because of, I mean, you need hydrogen first. It's first element in the periodic table, so that needs to come first, and that will always be your core energy production. So deuterium gets formed from hydrogen. Tritium gets formed from hydrogen or deuterium. So everything kind of follows from hydrogen. Because hydrogen has to be the base reaction in stars, they're kind of constrained by how likely the hydrogen reaction is to occur. In the field, we call it the cross-section. So the cross-section is how likely is a fusion reaction to occur between hydrogen and hydrogen. And that's very low for hydrogen. So that's kind of fundamentally why stars are so inefficient. One thing I would say is that it's a good thing they are, because if the sun was any more efficient, so if the sun was as efficient as a fusion reactor on Earth, it would have burnt up within millions of years rather than the billions of years that it's been going for now, and hopefully the billions of years that it will continue to go for. So it's a good thing that stars are inefficient. It's a bad thing for us because it means we have to come up with these other alternative fuel supplies. Good question, mate. That is a really good question, and I've never been asked that question before in a talk. So I always like questions that I've never been asked before.
Gosh, okay, thank you. Right, got some more questions coming up now. So how have robotics developed at JET, and have any other applications in physics or industry?
Yeah, okay, that's good. So we're not, one thing the fusion community is not very good at is selling all of the interesting things that come out of fusion. So I think I will answer this question, but I'm going to answer it slightly more broadly than perhaps it's been asked. And the question I'm actually going to answer is how does developments in fusion help other areas of society? And robotics is one of them. So JET has for a long time, it's kind of led the way in robotic maintenance devices, and particularly in robotics with really big, heavy, what we call boom robots. So these are robots on really long, heavy arms. It's led the world in that for a long way. And because of that experience, we created this center called RACE, which is Robotic Applications in Challenging Environments. So the idea of RACE is that it works on fusion robotics. So taking this idea from JET and expanding it to lots of other areas in fusion, but also a lot of the sort of things that RACE looks at for fusion are really applicable to other sectors. Like, for example, so basically they're applicable to any sector, any application where you have challenging environments, so really harsh environments that you don't want to send humans into. So I'm thinking things like nuclear fission reactors, right? Decommissioning of fission reactors. You don't want to send humans in to decommission fission reactors like Fukushima or others that have shut down. Space, if we could do a lot of repairing in space with robots and not humans, that would greatly reduce the risk of repairing satellites and space station, things like this. Accelerators, particle accelerators, they produce a rather harsh environment to send humans into. So there are all these different spin outs that we can do. One really interesting one that doesn't seem necessarily so natural is that so you've got this massive robot that's like eight tons of robot, and it's inside JET. JET is about a £2 billion machine, right? It's an asset that's worth about £2 billion. If this robot goes wrong, if the sensors on this robot are not sharp enough and you hit into the wall and you damage the wall enough to shut the machine down, that's a huge liability. So the sensor technology on these robots is really, really sharp. It's really cutting edge. And actually some of that sensor technology has since spun out and is now being used in autonomous vehicles. So artificial intelligence driven vehicles. So there's all these different technological spin-outs that are starting to happen from fusion, and they're really accelerating. There's more and more and more that we're seeing, more and more ways in which these kind of spin-outs can happen. It's like the Apollo program, right? The Apollo program was to send man to the moon, or sorry, send humankind to the moon. But along the way, they made so many contributions to society, and fusion is doing the same. It would do more if we spent 3.4% of GDP on it, like they did in the Apollo program, but nevertheless, fusion is doing the same.
Oh gosh, okay. You wouldn't expect it to have such an influence on other areas, would you?
Exactly. But it's really, it's we do a lot, and a lot of the stuff actually so Column UKAEA has 4 main goals, and its mission, so this UKAEA mission statement is to produce sustainable fusion energy, right, fine, and maximize the scientific and economic benefit of doing that. So it's really embedded in everything we do, that not only do we want to produce fusion, but actually we want all of the benefit that you get from doing the science, all of the benefit you get from developing the technology to really be maximized whilst we're doing it. There's real potential for doing that.
We've got some more questions, more around careers possibly. So what would a job at JET look like?
What does a job look? I'll answer this from my perspective in a sec, but there are lots of different jobs at JET. So I'm gonna take it from a kind of physicist's point of view. If I was a physicist now looking at a job in JET, there are various different areas I could look at going into. So I could look at, do I want to go into more of an engineering path? So do I want to look at actually building parts of the machine, or affecting parts of the machine, designing diagnostics, designing things to hold diagnostics? Do I want to go down that sort of road? Do I want to look at electronics? Do I particularly like electronics? Electronics engineers are really in short order, and physicists would be good at all of these sort of things. Do I want to go into research? And that's where I went. So I went into research. Do I want to research in plasma physics? Do I want to research in material science? Do I want to research in tritium science? All of these things are possible. What does the job on JET actually look like? So from my perspective, I'm a plasma physicist, and I'm going to take you through a sort of typical, the way I like to do this is I like to take you through I'll take you through a typical day, and then I'll take you through a typical experiment, because they're kind of two separate things. So a typical day is, you might have 2 or 3 different projects you're working on at any one point. So 2 or 3 different avenues of research. Some of those will be very computer-based. So a lot of what we do is very computer-based, because the experiments are so expensive to run. We have to do an awful lot in simulation first in order to check that when the experiments are running, they're optimized. So you might be designing simulations. You might be doing a lot of coding. You might be doing pen and paper, sort of chalkboard maths, in order to figure out if your experiment that you want to run is going to run the way it should. Lots of paper writing and writing academic papers, things like this. You might be designing your experiment. So a lot of preparation work goes into designing an experiment. You might spend a day thinking about, if I'm going to run my experiment for 3 months, how do I need to coordinate all of the measurements, all of the operation of the machine in order to actually run an experiment, right? All of these things need to be thought about. Now, let's fast forward to a second day in the life of a physicist on JET. So say you've done all that preparation, you've designed an experiment, and you're coming for a day in the actual JET control room, and you're going to run your experiment. What does that look like? Well, first off, one experiment on JET is not really one experiment. You get either a morning or an afternoon, and in that morning or afternoon, you can have probably up to about 10 individual experiments in your whole experiment, in your whole bundle of experiments. So you have essentially 10 opportunities, or a sequence of 10 plasmas in which you want to try and discover something. Now, what will normally happen is you'll come in the morning, the machine will be set up, all the magnets will be getting up to operations, heating systems will be coming online. There'll be a series of operators, so you're not the one that actually operates the machine. There'll be a series of operators, and you'll go and talk to the operators, dial in all of the settings that you want for your experiment, which you'll have iterated on beforehand, so you'll know what you're going to do. Dial in those settings. You'll also have a team of people who are going to take the measurements as well. So you'll go and coordinate with that team, make sure everyone's all ready and set up. The operators will start the countdown, and in JET, it's awesome because it's 1980s facility. The countdown and everything is kind of like Star Trek style buzzers and lights going off everywhere. Mast was a bit different because Mast was built later. It was a bit more boring. But yeah, JET's awesome for that. So the countdown will start, and when the countdown gets to 0, you will start seeing, after a few seconds, you'll start seeing a little flash of light on one of the screens, which as you watch it, it'll get brighter and brighter, and then you'll see something that looked very much like that movie that I showed you, and it'll last for about the same amount of time as that movie lasted. And that is one of your experiments, right? So once that's done, that's one of your experiments. Your challenge then is to look at the data from that experiment, decide if it did what you expected it to do, or if it didn't do what you expected it to do, and then come up with a plan for the next set in your sequence. Are you going to stick to your pre-prescribed plan, or do you need to change it? You have to do all of that decision-making in about half an hour, because in about half an hour, you're ready for your next experiment. It's a really cool environment to be in. David, I don't know if you want to say anything. So David actually helped me contribute to a couple of JET experiments when we were on the day. What was it like from your perspective, David?
Well, I was looking at the turbulence diagnostics, and so between each shot, I was loading up the data that was taken, analysing it, trying to see what the changes were. And the experiment that I was involved in, we were adding carbon into the machine to see what effect it had on the turbulence. And so I was producing various figures for looking at characterising the turbulence and passing them on to Nick and the scientific coordinator, and they were trying to decide if they were going to continue for the next shot to do what they had planned to do, or if they needed to change something because it does something they weren't expecting. And a lot of the time it does something you're not expecting. And there are people running around trying to decide what to do for the next experiment. And it's really exciting to be part of that.
Yeah, so it's a really cool thing, and it's really addictive. So I've run experiments on 4 different tokamaks. I've run them, the 2 in the UK, 1 in Switzerland, 1 in Germany, and it's a different challenge wherever you go. So on jet, you get a long time between shots. You get about half an hour, because in jet it gets hotter than anywhere else, so all the machine has to cool down. In Switzerland, you can get as little as 12 minutes. So you get 12 minutes to decide what you're doing for the next one, and that's a real challenge to kind of get everything decided and ready to go again in 12 minutes. So it's really interesting. It's one of the best bits of my job, is that sort of thing. That's not necessarily day to day, but that's what you're working up towards day to day. So a lot of your job then is all of the work that it takes to prepare yourself for that day when it's experiment day. Long-winded answer, I apologize for that. I get overexcited. I'll try and keep the answers a bit shorter.
No, don't worry. Gosh, I bet everyone here is dying to work at jet now. But another question was, how many people work at Culham, and then how many people do you think are going to work at the ITER?
Oh yeah, that's a good question. So Culham, at the moment, we have about 1,200. Well, let's see. We have about 1,200 staff. We have about 1,800 people that we might contract in as well, or that are seconded to us. So yeah, about 1,800 to 2,000 people at the moment work at Culham. So it's a big site. It used to be only about 500. So we've really grown in recent days, and it takes between 500 and 600 of those are dedicated to jet. So it's a big. There's a lot of people it takes to run one of these things. ITER will have a huge number more than that. But not all of them will be scientists. So a lot of the people that work on these machines are not scientists. They're staff dedicated to getting the project running, making sure its financials are all in line, management, engineering, making sure everything is running as expected. Operations is a huge part of the people cost. So there are lots and lots of different jobs. So, but ITER, yeah, it's going to be, I'd be surprised if ITER is under about 5,000. It's got 1,500 people working on it right now, so it's a big undertaking.
Gosh, yeah, okay. Next question, just to keep going, because there are quite a few, aren't there? Would it be possible for the energy produced to be ramped up or down to deal with change in demand? Do you think?
In principle, so probably what you'll do is you'll design a tokamak reactor that will have one way it works, and so you'll turn it on and it will produce a set amount of energy, and then you'll turn it back off. If you wanted to change in demand, then probably what you would do is you'd either turn it off. So fusion will there probably won't be any big country on earth that is ever fully supported by fusion. Probably the role fusion will play is you might have a whole portfolio of renewables, but you will need some sort of base load supply to sit underneath that portfolio and produce power when the sun isn't shining, when the wind isn't blowing. And you want that to be safe and not carbon reliant. So that's probably where fusion will sit into it. So what you do is you either turn the reactor on, you turn it off when you don't need it, or you have a power station where you have a series of modular reactors that sit around so that you can turn 2 on if you need extra power, you can turn 3 on if you need extra power. That's probably the way you do that. It's very hard to operate a fusion reactor like that in a way that you can just ramp it up or ramp it down, because these things are phenomenally sensitive. So if you do anything that is kind of outside what you can do with it, it will just fly off and you'll lose your plasma and probably damage the machine.
Okay. So, and also you seem to be making bigger and bigger machines, but would there become a time when they could be shrunk down?
Excellent question. So there's a good reason why they have to be bigger and bigger. Essentially, you're physicists, so I can get a bit technical with you. Essentially, the amount of heat you put in depends on the surface area of the donut, because it's the amount of heat that passes through a certain surface area. The amount of heat you get, the amount of energy you get out depends on the volume of the machine, because it's essentially how much fuel you have that's doing fusion, right? So volume scales like the radius cubed, surface area scales like the radius squared. So at the moment, I'm in a situation where the amount of heat I have is less than the amount of energy I'm producing. But if I just make my machine bigger, the amount of energy I'm getting out is going to increase faster and faster than the amount of energy I need to put in. So you make the machine bigger, then you can almost guarantee that you're going to be able to get more energy out than you put in. That's kind of, it's much more complicated than that, but at its core fundamentals, that's kind of why these things have to get bigger. But then the spherical tokamak is a way of then making that whole thing smaller again, because you've essentially got the same sort of plasma behavior, but you've packed everything into a much tighter space. So the spherical tokamak is a way that you can start making things smaller. Now, real miniaturization, like Iron Man style arc reactors in your chest, or put a fusion reactor on the back of your car, that doesn't seem possible at the moment. To do that, you need some real technological innovation, because you're fighting against this problem that I've just said about how heat and energy in and energy out scale differently. So really miniature fusion reactors don't seem like a viable route at the moment, but certainly in the future, anything's up for play. But yeah, at the moment they're kind of they're as big as they have to be, essentially.
Okay. Another question here is, what caused the difference between energy production before and after they replaced the materials at JET?
Well, that is a really interesting question. I see that's from Orlando. That's a really interesting question. And that is exactly what David and I were working on in this experiment that we worked on together with. So the short answer is we don't really fully understand yet, because the fusion all happens in the hot middle of the machine, right? It happens in the hot core. The hot core is quite far away from the walls of the machine. So why on earth, if I just change the wall from being made of carbon to being made of beryllium and tungsten, which is what it's made of now, why on earth would that change the hot core of the machine? We think we have some ideas, and basically it seems like, so whenever plasma hits a wall, hits a material surface, some of that material surface gives itself back to the plasma either by melting or by vaporizing in the case of carbon. And it seems like there was some benefit that we didn't really understand of having carbon in the plasma, having a small percentage of carbon in the plasma actually had a benefit. But because we'd always run like that, we didn't know that that was a benefit until we took it out. So what our experiment, what David and I were working on, was they were in the metal machine, we were puffing small amounts of methane, which is part carbon, part oxygen, small amounts of methane, part carbon, part deuterium. We were puffing small amounts of methane into the plasma so that we could reintroduce this carbon in a controlled manner. And we think that it was having some impact on the way turbulence works. And that turbulence was having some impact on how hot you could make the fuel get. So really, that's an active area of research. And there are kind of two lines of thought on this. One is we need to understand the basic physics behind it. And the other one is we need to do everything we can to tweak things until we get back up to the old performance.
Okay. And another quite interesting question here is, what is your favorite example of fusion in sci-fi, and what is the most realistic example?
That's okay. Let me share my screen again. Good question. So my favorite is also the most realistic because it's the most realistic. It's this one in the bottom corner. Anyone on chat, if you're looking at the screen now, who can identify what this is from. Put this in the chat if anyone thinks they can identify where this video is from. Yes, Will, exactly. This is from the computer game Fallout 4, Xbox, or I think PS4 I put it on. And this is a mission where you go to an old abandoned fusion reactor that's still running and you have to turn it off. First thing is, you don't ever want to walk inside a fusion reactor, that is for certain. But if you actually look at the fusion reactor in this video, so let's just let it loop around once more. actually look at the fusion reactor, look at the inside of there, and then if I go back up some slides, and we look at the inside of JET, look how similar the fusion reactor in that video looked to the inside of JET, right? Extraordinarily similar. The other cool one that not many people know about is this thing in the bottom left-hand corner. This is Interstellar. Now, you never see a fusion reactor in Interstellar. They never show you it. But if you're really geeky, you can look up online about their spaceships. And it turns out all of their spaceships in Interstellar were powered by small spherical tokamaks that would look something like MAST. So small spherical tokamaks like that were powering all of the spaceships in Interstellar. So yeah, I think they're my two favorites because, and I like them because they're accurate. Yeah, and I'll always have a place in my heart for the Mr. Fusion device from Back to the Future as well.
Oh, thank you for sharing that. We've got, I think, one more question. It's a little bit political, but now we've left the EU, is the UK going to be part of the ITER programme or not?
Yeah, really good question and very worth asking. So let's first off, let's handle the leaving EU part. So it's not the European Union itself that we have to be part of. It's it's Euratom that we have to be part of to be involved in ITER. And Euratom and the EU are separate, but in divine wisdom, when we left the EU, we also left Euratom. So we're now, or we will be leaving Euratom. So we're now UK government negotiating a way of us, or trying to negotiate a means by which we can still be part of Euratom without being part of the EU. Because if we can be part of Euratom, then we can still be part of the ITER programme. And that's kind of fundamentally where we are at the moment. So those negotiations are ongoing. There's also a second interesting aspect to that, which is that JET, which is Joint European Torus, is the only case where there is a bilateral, which basically means just us and them, agreement between the UK, scientific agreement between the UK and the European Union. So that is a whole separate can of worms that's being worked out at the moment. But there is really, really strong will on both sides to remain part of the ITER programme. So we want to remain part of the ITER programme because we recognise how important it is to fusion. And we've had a big role in the ITER programme so far. One of the really senior people is British. And ITER want us to be part of the ITER programme because it's hard for me to say this without sounding biased, but UKAEA really is the world leader in fusion. There are a few reasons that that's true. First off, we're the only place that has two big tokamaks, so that immediately makes us unique. But we're also the only place in the world where you have fusion experts. You have people like me who study heat exhaust, heat removal. You have people who study tritium. You have people who study robotics. You have people who study materials. You have a whole engineering staff. We're the only place in the world that has all of that on one site. So at the moment, we really are the experts in the world. If you go to Japan and ask Japan who are the experts in quantum computing, they'll say Japan. If you go to the US and say who are the experts in quantum computing, they'll say the US. If you go to US or Japan and say who are the experts in fusion, they'll say UKAEA, they'll say UK, because unequivocally we have all of these expertise. So, and ITER recognizes that, right? So ITER wants us to remain in ITER because they want us to contribute to the remote handling. They want us to contribute to the tritium systems. They want us to contribute to the plasma science because they recognize that we have these kind of unique expertise to do so. Every single contract that ITER has put out in robotic maintenance to date has gone to the UK via our centre RACE. So either RACE will help in some way in the project or it's helped to barter that contract. Every single one. And we're expecting similar levels for all of the tritium contracts that ITER puts out as well. So there's really, really strong motivation on both sides for us to remain part of the ITER programme. We just have to make sure that that comes through in the negotiations. And at the moment, we think it will. Yeah, so the UK is certainly planning on remaining part of ITER. ITER is planning on the UK remaining part of ITER. It's just as long as nothing completely crazy happens from the negotiations. which is well outside my area of expertise. And the actual negotiations, I definitely can't give you too much insight there because I don't have it myself.
Oh, fair enough. How inspiring it is, though, that the UK is leading fusion. I hope everyone here listening in is going to continue this trend and keep the UK ahead of everyone else. But I think that's all our questions now. So thank you so much. And I know Will wants to also say another thank you.
Yeah, hi again. Thank you very much for such an excellent talk. I've had a great time myself, and I'm sure everyone else has as well. So I think all that's left to say is just so everyone's aware, this has all been recorded. So if you want to go back and watch it, feel free to do so. It should be available at some point, either later today or probably tomorrow, more likely. But well, thank you again all for coming, and thank you again.
Wonderful. Can I just finish? Can I just finish by saying one thing?
Yeah, absolutely. Go for it.
So we were saying we want to remain fusion world leaders, and I think we will, because the fusion program in the UK, I was saying about STEP, it's expanding massively, right? UKAEA, we've grown by about 30% this year, and we'll probably grow by about 30% again next year, which for anyone that knows anything about businesses, that is just an insane year-on-year growth, right? That's really, really insane. The only way that we can keep growing like that, and that fusion in the UK can keep leading the world and keep doing what it does, is if clever people come to join us and come to help out with the fusion mission. So if any of you are even in the slightest bit interested in coming and working on fusion, coming and seeing what we do, get in contact with those with the email addresses on the slide, or ask Will or ask Nick for my email address. I'm more than happy to act as a contact. And come and ask us about what we do. Ask us how you get involved. We've got graduate schemes. You can do PhDs. There's other entry routes. And when we're all back in and actually able to walk around and stuff, come and visit site. Come and see what we do. It's really exciting, and it's only getting more exciting. So yeah, please, if you're interested, come and see what we do. Come and get involved. And thank you guys for organising this. It's really real treat to talk to such an interested group of students. And Eden and Will, you've done an extraordinarily good job of organising this and keeping it well organised. I've been in much more shambolic meetings than this, even when I can see people face to face. So you've done a really good job. Thank you very much.
Thank you.